Okay, so I did a much more cleaner version of yesterday's lesson for my afternoon period. And then turns out I didn't click record. So everyone's stuck with the not so clean lesson. Sorry about that. Let's make this one a little easier, okay? A little bit better. So again, to talk about or to continue off of yesterday's conversation, remember if we did have a graph, so suppose you made an investment of money knowing it will double in value every year, which obviously doesn't work that way. But if it did, wouldn't that be amazing? And now here it is. If it doubled in value every year, starting from a time of 0, okay, it would shoot up super, super fast. And we know that time is going to be the independent variable. Independent variable would be time. That means your dependent variable would be money. What if you were interested in the relationship as an inverse direction, so an opposite direction? You would then use the money to calculate the time, which is an inverse. It is not easy to receive an answer and then guess the question. So it is to our benefit if we calculate a new inverse equation that gives us time value for any money. Long story short, sometimes it's very difficult to receive the answer and guess the question. So it's always nice to take, let's say something like this, right? Don't write this part. It's a lot nicer to switch the location of your x and y and then rearrange it so that we have an equation for ourselves, right? That was the whole point of learning how to do inverse in grade 11. And if we successfully did that for time versus money, it would be money versus time, right? And that is our normal conversation, to be able to take our x and y axes and flip them. The problem is when we reach exponential functions as your parent function. And that is, if I were to switch my x and y, I would get x equals base to the power of y, and I need to get y all alone? How? That's my issue, and that's my problem. And that is the reason why we have this new system we are going to introduce. It's called logarithms. So let's read the question. Let's read the sheet. Right now, the bordered equation states to produce x money, everyone follow along with me, to produce x money, the base b must be raised by an unknown y number of years. However, by convention, it's always nice to have y all alone. And so we introduce and rewrite this new equation as that. So the best way to read this is something like this. This is all just, a handout. But let me try to write it in this way. If I have some base to some exponent, and that gives me some answer, a logarithm is, I have the reverse of an exponent, or the inverse of an exponent. I have a logarithm, and the exponent used to be of some base. If the answer was this, what was the exponent? That is how we are rearranging the equation. I know it's a little confusing. We're going to have to get used to it slowly, all right? So here are some examples. 2 to the power of 3 is 8. In a log with base 2, if the answer was 8, what is the exponent? I know it's a mouthful. I'll say it one more time. With a base of 5, if the exponent is 2, the answer is 25. With the base of 5, if the answer was 25, the exponent must be 2. Okay, that's basically what we're saying. There's no rearranging like we did for quadratics, no rearranging like we did for rational, linear, any of the stuff that we did even yesterday. There is no easy way to reverse or inverse an exponent other than to introduce a completely new function. And that function is what we looked at yesterday. That's what a log looks like, log of some base. All right, the y value is log of some base with the x going in. So the textbook definition is the logarithmic function is defined as y is equal to log of x using some base, or y equals the logarithm of x to the base b. And of course, the base can't be 1, and the base has to be a positive. Put a little star next to that. What do I mean by that? If I have 1 to the power of 5, 1 to the power of 6, 1 to the power of 100,000, whatever, they all equal to 1. So that's not really a function. Okay, the base cannot be equal to a 1. At the flip side, the base must also be positive. And you want to think about that? I'll come back to this after the lesson, okay? Why is it that a base has to be a positive? We'll think about that. Okay, just as positive is to negative, think of logarithms as the opposite operation of exponents. So this is more conceptual, more theory. Let's do some practical questions. Rewrite the equation in logarithmic form. And this is why I can't have you using a calculator for the quiz. I need to see that you can take an equation, an exponential, and turn it into a logarithm. 16 is equal to 2 base 2 to the power of 4. So change that into the logarithm narrative. What's the base? 2. So using log of base 2, what's my answer? If the answer is 16, the exponent is 4. Okay. So let's try to use these words, these specific words. Y equals the logarithm of x to a base b. So here, m is equal to n to the power of 4. That means the log of m to base n is equal to an exponent of 4. That's what it would look like. And same thing. Okay? Just in case you get confused, remember that's the base, that's the exponent, and that's my y value, right? That's my answer. So if it's 3 to the power of negative 2 is equal to 1 over 9, then log of 1 over 9 with base 3 means the exponent must have been negative 2. So we're just going in reverse. We have to get used to using logarithms. There's no, I'm going to say, there's no easy way around it. Okay? So, yes?
For this one, the words 1 over 3, 1 over 9 equals
1 over 3? Yeah. The base?
Yeah, the base.
Using a base of 1 over 3? If the base was 1 over 3, the exponent would be positive 2. That's right. So if you want, you can say, this is going to get wild. If this was the question, you would say log of 1 over 9 with a base of 1 over 3 means the exponent is 2. This and that is actually the exact same thing, right? Oh, yeah. That's right. Okay. So why is this important? Well, just as an example, okay? I'm gonna just make it painfully obvious of why this might be necessary. If you have 10 to the power of 1, oh, sorry, yeah. Let's say you have, why is this useful? If you have log and your calculator only does log of base 10, okay? And you plug in some number, it's gonna spit out another number for you. So if you say you have log of base 10, log at base 10, and the answer was 10, what was my exponent? be 1. Why? Think backwards. That means you're saying 10 to the power of 1 equals 10. If I have log of base at base 10, and the answer is 100, what was my exponent? 2. What you're saying here is 10 to the power of 2 gave me an answer of 100. Okay? So you could say, oh, that's, Mr. Kidd, I don't need logarithms per se. I can predict, it's not a difficult thing. Right? It's not a difficult answer or whatever. What if the exponent, I didn't know, but it was very important for me to see what the exponent was because the answer was like 1.975. Let's say in a scientific experiment, this was what you measured, and you know it was 10 to the power of something. Like, how do we get there? So we need to say, okay, log, using a calculator, using a computer, because a computer is able to generate everything for us very quickly. If I have, with a base of 10, my answer was 1.975, what does my exponent have to be? Well, clearly, it's going to be smaller than 1, right? Because it has to be smaller than 10. So you take your calculator, and let's use it now. See if you get the same answer with me. Again, your calculator should have a logarithm already inputted and programmed to be base 10. So when you press the number or press the log button, it won't show a base. It's assumed that you know it's 10.
Does it matter if it's in radian?
Not in this one. Okay, so log of 1.975, and you should get, I don't have enough space here, but I'll write it, 0.295567, and if your computer gives you more, 0.9996 something, something, something. So let's round that to about 0.296, approximately. Okay, so 10 to the power of 0.296 gave you that number. Being able to work in inverse is going to be a useful tool in a variety of different math applications. That's it. Okay, so before we get a chance to do some more complicated things in the end of chapter 6, I need to make sure not only do you see and understand the meaning behind every number, but you're able to go between exponents and logarithms without much brain power. Okay, so some examples we can do together. How about I do ACE? I will summarize the lesson, and the rest of the class you can work on your the extra sort of practice sheet I gave as part of the package. Okay, just work on it. ACE. Maybe not ACE. Let's just work on everything. Would you like an opportunity to try it? Should I give you about 5 minutes, right? And just, it's either you got it or you don't, and you just keep practicing. How about I pause the video and give you some time? Okay, coming back. At least for the first 3 questions, let's get it through. Once again, if you were to solve this without a calculator, being the first time with logs, I think it's very understandable that you would think about it as an exponent. So log of 81 with base 3 is like saying 3 to the power of something is 81. Using your multiplication skills, I'm hoping you got the idea, or right, 3 times 3, 9, 27. Yeah, I think you're able to determine x would equal a 4. Therefore, a log of 81 at base 3 is also equal to 4. Same thing here, right? 2 is my base because log is base 2. It means the exponent is base 2. My answer was 1 over 8. What was my exponent? So again, without a calculator, I have to turn this into the reciprocal, 1 over 2, right? I need to somehow turn that into 1 over 2, and then 2 becomes an 8. So the quantity will be negative, and the value of x with a negative, that will be a 3. So I know this would answer negative 3. It's just deduction, I suppose. Same thing here. Think about it. If it's base 10, because log is base 10, the exponent is base 10, x is the exponent, my answer was 0.01. The number is getting smaller. Maybe this will help. 0.01 is the same as 1 over 100. That means whatever the x value is, the base must have turned into 1 over 10, and then 10 was multiplied with itself to become 100. X is going to be -2. Okay? There's just thinking about it in this way, and you keep on chewing on it, I think it'll be a lot faster and a lot easier to sort of approach logarithms in a variety of angles without stressing out. Rewrite the following in exponential form. Let's get this very quickly. Once again, log of base 4, that means exponent, base 4. Answer is 3, means the exponent was 3. Answer is 64. Log, if there is no number, by default, it's base 10. The answer was y, so that means the exponent is y. Here, it's log of x, so that means the exponent or the power must have equaled x. Base is 2, exponent is 5. Answer was 32. Base is b, the answer was w. Answer was w, so z must be. Is there an easy way, like a jingle that we can say to make things easier? Base was 2, the exponent was 5, and the answer was 32. Base was w, exponent was, base was b, exponent was w, answer is c. Base was 10, the exponent was 2, the answer was 1 over 100. Base was 7, the exponent was 2y, so the question, the answer must have been x. Again, yeah, just to make things interesting, why not try that little code thing? Anyone remember SPY versus SPY? Anyone? No? So that little weird picture on your practice sheet on the back of this package, you don't know where that booklet that came from? Anyone know those two figures? You've seen it before? They used to be, I think, the poster faces for Mad TV's little skit as well, but it's also from a Nintendo game, like 30 years ago. So, anyways, in summary, a logarithmic function is the inverse of an exponential function if we are dealing with an exponential function. It would look something like that, right? Y is equal to b to the power of x. What's interesting is, I'm going to try to mirror image this. If I were to deal with the logarithm, the base parent function of a logarithm is like this, and y is equal to log of x with base b. And the part that you must be careful of is the x of here is now the y of there. And the y of here, let's see if I could use a different color. Nice. The y of there is now the x of there. They are switched. And as you know, it's reflected on that y equals x line. Okay. So in summary, the idea is just y and x is switching. The hard part is there is no easy way to do it. We must introduce a completely new parent function. And with a new parent function, what do you think is the next logical step in our learning? Yeah. So 6.3 is going to be knowing how to identify some accuracy points just like you did in grade 11, and applying AKDC. Okay? So please, whether it's textbook or the sheet that you have behind you, get some practice, switch between exponential and logarithm, and for the sake of the quiz, try not to use calculators unless the numbers I give you are in crazy decimals and there's no easy answer to it. Okay, no fractions, no whole, no roots, no exact values you can find. Okay, try to not use your calculator for today. Any questions? Okay, with that said, just to make it clear on the video too, you have a, let's stop sharing and I will share this screen instead. Entire screen, sure. As a reminder, we have our quiz for 6.1, 2, and 3 on Monday. And since we have our Thursday and Friday free, we are still going to go into what I'm going to consider the main, I guess, quote unquote, difficult part of chapter 6, right? And there's a little, and just be aware, 6.5 is basically A rock, I rock again. Okay? So it just, the main part is 6.4. So we are going into 6.4, but you do have a quiz on this stuff Monday. And then you're probably going to be studying your butt off for 6.4 in preparation for the test. Please be advised, if you were stressed out yesterday because you had so many evaluations next week, what was 6.1? Exponents. What is 6.2? And then what's tomorrow, what I said? That's majority of your quiz. It's doable. It's manageable. You can do this. Next week will not be as scary as you think. Just plan your time wisely. Any other questions? Yes? No, but I will scan it right now. Anyone else? Okay, if that's the case, I will stop this video and away you go.